product formulas. Sorry. So today's topic is spectral analysis of product formulas for quantum simulation. And this talk is based on some of the joint work with Professor Elizabeth Crosson, and we're both members in CQIP. So now let's begin with some discussion about quantum simulation. So quantum simulation is one of the most interesting and promising applications of quantum computer. And the task of quantum simulation is to construct the time evolution operator in terms of only local unitary gates. So basically, we want to solve this Schrodinger equation, and in the matrix representation, it is equivalent to construct a good approximation of this unitary for some Hamiltonian h and some simulation time t. There's a lot of reasons why we care about this application, because we care about this task because it has a lot of applications. For example, in quantum chemistry and condensed matter physics, we can use it to predict the properties of some material. In high energy physics, we can use it to simulate lattice gauge theory. So for now, there are already different types of quantum algorithms for it. We have product flow method, linear combination of unitary method, quantum signal processing method. And in today's talk, we are focused only on the product flow method. And it is very concise and efficient algorithm, but some of the results can be generalized to other quantum simulation algorithms. So here is a very short introduction to the total formula method. In quantum simulation, eventually we want to approximate a large unitary. And we first separate the unitary into small pieces and replace each short-time evolution with a good approximation of it. So here, the linearity is our total simulation time. Big R is the total number, which is how many slices we have, and delta T is the total step. And using the total Suzuki formula, we can approximate each short-time evolution with only local quantum gate. And here's how we do it. So for a general normalized Hamiltonian, which is the summation of local terms, we first separate the local terms into different layers, such that each layer is a summation of only local commuting terms. And then the first order formula will give us this as a good approximation of a short-time evolution. And because each H gamma is only a summation of local terms, we can only use local quantum gate to construct it. And to determine how many resources we need in this algorithm, we should do some error analysis. And the error of this method usually is quantified by considering the non-distance between the digital operator and the ideal evolution operator. And this operator norm here is defined as the largest singular value of a matrix. So there has been a standard way to choose this non-distance. We can first relate the overall non-distance to the total error of a single step, and roughly they satisfy a linear relation. And because delta is very small, we can quantify this term efficiently. And finally, based on a proper estimation of the error, the total simulation time, and Hamiltonian, we will determine what is the proper choice of the total number. And total number is directly related to the circuit depth of this algorithm. So for the first order formula, epsilon is proportional to R times delta T squared. So reversely, the circuit depth is proportional to T squared over epsilon. This is how many resources we need in this algorithm. And in the left-hand side is a list of notations. In the right-hand side is a simple illustration of this algorithm. Where the Hamiltonian we simulate is H1 plus H2 plus H3 plus H4, where we first separate the local terms into two layers, and then the first order formula will give us this 4 quantum gate as a good approximation of a single time evolution. If we repeat this procedure again, eventually we can simulate this evolution for a very long time. So actually the analysis about the total formula has been very mature, but today we'll try to provide a different perspective and achieve some improvements in special situations. So instead of considering the non-distance between these two unitaries, we can also separate the error into fidelity error and phase error defined as follows, whereas F is relevant to the fidelity between the digital evolved state and the ideal evolved state. And the theta is the relative phase between them. So we can prove that when the non-distance error is not too large, these three quantities roughly satisfy a linear relation. So this means that in general situation, the estimation of delta is already a good estimation of F and theta. So there's nothing interesting here. But theoretically, it is totally possible that the fidelity error can be a lot smaller than the non-distance error, because the digital error can be dominated only by the phase error. And actually, a trivial example is when the initial state is an eigenstate of the original Hamiltonian. So to see so, let's formally introduce the method we use, which we call the effective Hamiltonian method. So each total formula can be considered as a short-time exact evolution under the effective Hamiltonian defined as follows. Then using this notation, we can see that the digital operator is just a long-time evolution under the effective Hamiltonian, which has a slightly different energy level and different eigenbasis. So using the BCH formula, we can see that the perturbation part in the effective Hamiltonian will look like this, whereas H gamma is the local layer in the product formula. And as you can see, when the shorter step goes to 0, the effective Hamiltonian is exactly the same with the original one. Now let's use this to analyze the previous question. Suppose our initial state is an eigenstate of H. We first project the state into the effective eigenstate of the effective Hamiltonian, which is also an eigenstate of this digital evolution operator. Then after the evolution, we project the state back to the original eigenbasis. As you can see, in this entire process, the fidelity error only comes from the first procedure and the last procedure. It can be irrelevant to how long the evolution is. It's only relevant to the deviation in eigenbasis. And on the other hand, the phase error is relevant to the short error in energy times the simulation time. And because we already have a good expression of the effective Hamiltonian, then using the Wiles inequality, we can also estimate the deviation in energy levels. But because of the specialty of this perturbation, it turns out the actual perturbation energy can be a lot smaller compared to this estimation. And here's where the improvement comes from. So in perturbation theory, we know that the first order perturbation energy will look like this, where phi air is the host mute. What happened? Okay. What happened? Okay. Wow. Okay. Can you hear me? Wow. What happened? Okay. Okay. Wow. So if the first order term vanishes, then of course the perturbation energy will have order v squared instead. So in our problem, suppose the leading perturbation term of the effective Hamiltonian is off diagonal in the original eigenbasis, then which means this relation, then of course the short error in energy will be reduced from delta t to delta t squared. And this relation, it turns out to be typical for the first order product formula. And now recall that the leading perturbation term in the effective Hamiltonian will look like this. And the first special situation is a two-layer case, which we separate the Hamiltonian into two layers. Then actually every two local Hamiltonian can be separated in this way. Now let's look at this expectation value. Because HB commute with itself, we can add an HB here. Then this part is just H commute with HB. And phi air is eigenstate of H. Now if we expand this commutator, we can easily verify that this is 0. And the second special situation is real Hamiltonian. So in linear algebra, we know that every real symmetrical matrix can have real vectors as eigenstate. Now let's compare these two numbers. The matrix are real, the vectors are real. This must be two real numbers. And at the same time, they are complex conjugate to each other. We have two real numbers, they're complex conjugate to each other, they must be equivalent. In this, we will prove that in both very general situation, the leading perturbation term is off diagonal in the original eigenbasis. And the direct application of this improvement is in quantifies estimation, where we start with an eigenstate of the unitary with eigenbase e to the I2 pi theta. And the purpose of the circuit is to extract the information of theta. Our final measurement outcome is actually the integer that is closest to 2 to the n times theta, where n is the size of the first register. So because the size of the register is finite, there must be some intrinsic precision of this algorithm. And if we use short formula to approximate u, there is also some short error in the final phase. And if we want to make sure the short error in the phase is smaller than the precision, otherwise the short error will be detected, the requirement on the shorter step and shorter number will look like this. And here, this here is the circuit depth to construct a single unitary. As a comparison, without the previous improvement, previously the shorter number is inversely proportional to C. Now it's inversely proportional to the square root of C. So we can also use this perspective to analyze a more general situation. And to do so, we introduce the two operator, where the D operator encodes the deviation in energy levels, and S encodes the deviation in eigenbasis. And so that the digital evolution operator can be written as follows. And then if we further assume that the initial state stays in a small subspace, then the short error can be separated into two parts. The first part is only relevant to S, which is a function of the shorter step. The second part is relevant to the deviation in energy level times T. As you can see in the large T region, only the second part is important, so the short error can be dominated by this term. And this perspective can help us to see the similarity between the first and the second order formula. So the second order formula has this expression, which is basically the product of two first-order formula, but one of them is reversely organized. It has been proved that the second-order formula error is proportional to error times delta to the third. And with the improvement in the short error in energy, we can obtain a similar result, where the first term comes from the deviation in eigenbasis, and the second term comes from the deviation in energy levels. And especially when the Hamiltonian is separate in the two-layer case, we can see that the effective Hamiltonian of these two formulas, they only differ by a small unitary. They have exactly the same energy levels. So in the large time region, they are very close to each other. Then after the analysis about the time-independent situation, now let's focus on the time-dependent Hamiltonian simulation. So if we want to simulate a time-dependent Hamiltonian using the short formula, the first two steps is exactly the same. We write the unitary as a product of a list of short-time evolution. And using short order decomposition, we approximate it with only local quantum gate. But because this is a time-ordered evolution operator, we still need to approximate it with time-independent Hamiltonian evolution. And the error in both procedure has order error times delta squared, like the time-independent situation. So even if we can capture the influence of short-order decomposition with the effective Hamiltonian argument, there's nothing we can do about the second procedure. So our method does not apply in general situation. But however, we do find a special situation such that we can only use effective Hamiltonian to describe the entire error. And this corresponds to the simulation of adiabatic evolution. So the idea of adiabatic evolution is we have Hamiltonian that evolve with time very slow. And the initial state is the ground state of the initial Hamiltonian. Because the evolution is very slow, approximately at every time, the evolved state is the ground state of the current Hamiltonian. So this is an example of linear adiabatic path where the big T is the total simulation time. It also quantifies how slow the evolution is. In the adiabatic limit, when T goes to infinite, the corresponding evolution operator of this Hamiltonian can transform the ground state of initial Hamiltonian to the ground state of the final Hamiltonian exactly. But in practice, we can never set T as an infinite number. It can just be a very large finite number. So there must be some difference between the evolved state and the ideal state. And this error is quantified by adiabatic theorem, which is a statement about the fidelity error between the evolved state and the ideal final state. So the adiabatic error can be quantified by a complicated function of T and H, where H is the normalized Hamiltonian. And approximately, in a simplified situation, it is proportional to H prime and inversely proportional to T times lambda, where lambda is the energy gap of this normalized Hamiltonian. So here's, now we want to construct this operator on a quantum circuit, and here's how we do it. We first approximate the ideal adiabatic operator with a product of a list of unitary. Each unitary is an exact evolution of a Hamiltonian at time step SG. And then we do short decomposition to each of the unitaries and product them together. We have our shortwise adiabatic operator. So eventually, we want to compare the difference between the state generated by this operator and the ground state of the final Hamiltonian. So in standard analysis, we can separate the error into two parts. The first part comes from adiabatic theorem. That is to say, even if we can construct this unitary operator efficiently, there's still some difference between the evolved state and the ideal state. And this error is estimated by adiabatic theorem. And the second part of the error comes from the short decomposition. It is the difference between the digital evolved state and the ideal evolved state. And it's bounded by the norm distance between these two operators, approximately is proportional to T squared over R. So it is natural to combine these two parts together as an estimation of the entire digital error, which is the difference between the state we generate and the state we want. But however, using the argument of effective Hamiltonian, we can derive another completely different upper bound. So now let's again consider the shortwise operator as an exact evolution under a slightly perturbed Hamiltonian. So in this perspective, the shorter adiabatic operator is just the discrete version of a continuous effective adiabatic path. So if this adiabatic path further satisfies the boundary condition, which says it has the same initial point and the final point compared to the original adiabatic path, then this operator can also send the ground state we prepare to the final state we want. So it's natural to directly apply adiabatic theorem on this new Hamiltonian as an upper bound of the entire error. But for now, there's still a very important issue, that is, why we can consider the discrete adiabatic operator as a good approximation of the continuous version. What is the criteria that enables us to do so? Well, it turns out there's a simple mechanism behind it. So to see this, let's consider a discrete adiabatic process where this is one state of the initial Hamiltonian. This is the discrete adiabatic operator, which is the product of list of unitary. And its inner product to the final ground state is the square root of 1 minus the adiabatic error. And because adiabatic error is not zero, there's also some amplitude to higher energy levels in the final Hamiltonian. There's also a relative phase between these two states, which is called the theta A. And our conclusion is the function that determines the phase is a lot different compared to the function that determines amplitude, in the sense that one does not allow time step to be large, but another one does. And here's the meaning of it. So using linear expansion, we can see that epsilon L can be, up to the first order, it looks like this, where L is the total simulation time, the number of steps, G is the index of the time step, lambda is the energy gap difference, and the T is the total simulation time. So in the continuous limit where L goes to infinite, epsilon L can be written as follows. And then using the Riemann-Lebesgue lemma, we can prove that the amplitude of epsilon L match with the prediction of adiabatic theorem. Now the question we want to ask here is, if we want the discrete summation to be a good estimation of its continuous limit, what is the requirement on the time step? The result is actually pretty surprising. And to see so, let's consider a special approximation where the amplitude is a constant and the phase is a linear function. And for this special situation, we can calculate the continuous version and discrete summation analytically. Now we want to compare the amplitude to find out the region that makes the discrete summation a good estimation of the continuous limit. It turns out, because of the specialty of sign function, as long as the time step stays in this very large region, the difference between them is just a factor of 2. But in numerical analysis, we don't care about this factor of 2. We only care about the dependence on T and L. On the other hand, the function that determines the phase, it's just a number function. So there's nothing special about it. And so the error estimation does not allow the time step to be large. Essentially, this is the reason why the norm distance error can be large, but the fidelity error is small. So this is basically today's talk. Here's a quick summary. We have a list of small results. So first, because of the perturbation part, because of the specialty of the perturbation terms, the deviation in energy levels can be a lot smaller compared to the wild inequality. And in some limited cases, the short error can only be determined by the deviation energy times T. And in the time dependent situation, by considering the digital adiabatic simulation as a discrete process under the effective Hamiltonian, we can directly apply adiabatic theorem on the new Hamiltonian as a new estimation. The reason we can do this is, analytically, we prove that a large class of discrete adiabatic process can allow the time step to be large because of the specialty of Riemann-Lebesgue lemma. So that's basically today's talk. Thank you very much.
Questions for Changhao? Come up and ask. Maybe I can get us started. Do your techniques extend to imaginary time Trotter formulas?
Yeah, I think so. If we can still use the effective Hamiltonian, as it's some of the result can be naturally generalized. Yes, I believe so.
Thank you. If there are not further questions, let's thank Changhao again.
Thank you. Okay.
We have a few minutes, so we should probably start on time. So we have maybe one thing is that I'll give you a 5-minute warning, and when you see 0, I'll